Hey. All right. Chapter 7. I don't want to yap too much. Just wanted to give you a little bit of an intro into what we're going to be doing in Chapter 7. So it's really going to be a departure from what we did in Chapter 6. And some of you are going to be so happy that we're in Chapter 7 because Chapter 6 tends to be more challenging just because it's applications. And anytime we're doing word problems and applications, students tend to get a little bit more frustrated because your setup has to be just right. What we're going to be working on in Chapter 7 is techniques of integration. So that means every section that we work on, we're going to be learning a new type of integral that you're going to see, so that when you encounter it, you'll know how to handle it. Really, in Calc 1, when you learned integration, you didn't learn a lot. You learned about the power rule to integrate. So you added 1 to the exponent divided by the new exponent. And then you just sort of undid derivatives. So you had, for instance, forms for derivatives, like for trig functions and then for inverse trig functions. And then you kind of undid those. We're going to be looking at a lot of different types of integrals in Chapter 7 so that you'll be seeing more and more things that you can do with integrals. And what we're going to start out with today is integration by parts. Next week, we're really going to pick up on some of this trig stuff, not only integrals involving trig functions, but integrals that can be rewritten to trig functions. So starting out with an algebraic integral and rewriting it in terms of trig, and you might be wondering why in the world would I ever want to do that? Well, you'd be surprised how helpful it can be. So today we're going to start with integration by parts. Now your text, if you look at the e-text, they have a really nice layout where they derive integration by parts and kind of explain where it came from. If you are interested, if you don't care and you just want to use the formula, that's fine. That's what I'm going to give to you now. So this is 7.1, integration by parts. Literally just got off the Peloton like 15 minutes ago. I'm very sweaty and gross. It's one of the nice things about working from home. Nobody has to smell me right now. All right, let me give you the theorem. If u and v are functions of x, and have continuous derivatives, then the integral of u dv is uv minus the integral of v du. My focus here. Okay, that's the formula that we're going to be using throughout this section. And this is going to look weird to you because you're like, what the heck, u and v? I don't get it. Well, like I said, if you look in your book, you're going to be able to see how they derive this. But basically, this comes from the product rule. So if you'll remember from Calc 1, we didn't have a product rule for integration. This is sort of like our way around that. This comes from undoing that product rule and just sort of applying it to the techniques of integration. So really what we're going to be using this for is situations where usually you have the product of two functions. Not always, but usually. I'm going to give you an acronym. And I'm going to explain how to use it in a minute, but I want to make sure it's in your notes because I feel that it's a really helpful acronym. It's called LIAT. L-I-A-T-E. The L is for logarithmic. The I is for inverse trig. The A is for algebraic. The T is for trig. And the E is for exponential. Now, if you're wondering what the heck is Lyot and why would I need to use this? Well, what we're going to be doing is we're going to be looking at integrands that are mainly going to be the products of functions. And what Lyot is going to do is it's sort of going to guide you to determining what function u should be versus what function dv should be. So imagine that your integral is given to you in the form, and it will be u dv. This is the order in which you're going to choose u. I'm going to write order for choosing u. Now, I don't want you to feel like this is always going to be the order all the time. There are going to be random weird exceptions to this, but for the most part, if you have a logarithmic function in your integrand, that's going to be what you're going to name u, and then the other function is going to be your dv. And so algebraic is further down the list. So you're used to seeing these algebraic functions, some sort of power function, x to some power. But that's further down the list. Exponential is going to be your last choice for choosing u. And I'm going to show you kind of why you're going to see this. What we're looking for here for choosing u is you want some derivatives that are eventually going to terminate. And like I said, you're going to see this as we work through the example. But really, dv should be like the most complicated portion, and u should be the portion whose derivative is the simpler function. So I'm going to say normally we're going to choose u to be the portion whose derivative is simpler. Normally choose u to be the function whose derivative is simpler than the original. The original function u. So u is going to be a function that has a derivative that's simpler than itself. dv is generally going to be the more complicated portion in the integrand. So dv will be the most complicated portion that fits an integration rule. If you can't integrate it, then it can't be dv. So you have to be able to at least know how to integrate whatever you're choosing to be dv. So these are your guidelines for what you're going to do as far as assigning which function is going to be u and which one's going to be dv. So u is generally going to start in this order. You're pretty much never going to see an exponential be u, but that's neither here nor there, I guess. I'll show you with some examples. So you're going to use this order, Lyot, for choosing u, and then keep in mind that u should be the function whose derivative is simpler. dv, you need to be able to at least integrate it in order for it to be dv. I will show you how this works in example 1. We're going to find the integral of 2x e to the 3x dx. So this is not something that you would have known how to integrate before hitting this section. You knew something about how to integrate e to the 3x. When you took Calc 1, you probably used a u substitution for that. We're probably going to be using that 1 over k e to the kx formula a lot. So I'm going to remind you of that right now, actually, just as a side note. The integral of e to the kx dx is 1 over k e to the kx plus c. So we're going to be using this throughout. just because we're going to be dealing with a lot of exponential functions that have some value of k that's not equal to 1. However, you have not yet had to deal with a situation where you had this exponential function multiplied by a linear function. Now, if the 2 is bothering you, no big deal. You can just pull that outside of the integral. And then you can really focus on what's inside your integrand. So I'm going to look at my integrand and I'm going to assign u and dv according to the rules that I outlined above. So according to Lyot, I'm looking for a logarithmic function, which I don't have, an inverse trig function, which I don't have, or an algebraic function. I do have that. That's the x portion. So this is very likely going to be my u. But thinking about my other note, u is going to be the function whose derivative is simpler than the original. Well, if I let u be x, the derivative of u is just 1 dx. So that is definitely following that rule. Now, if I let u be x, remember we're kind of matching this up with the formula that I gave you in the theorem, then dv has to be the rest of this. Now, you guys aren't used to thinking about like a d something as being more than just that notation. But what we're going to do is we're going to let the rest of this function be dv. So I'm going to let x be u, and then the rest of the function is going to be dv. Now remember that dv has to be the more complicated function that fits an integration rule. This does fit an integration rule because we can integrate e to the 3x dx. I just gave you the rule right here, but you could also use a u substitution like you did in Calc 1. So I'm going to let u be x, then du is dx. So we need those two things. And then we're going to let dv be the other piece of your integrand. You have to make sure everything is covered. So we use the u, everything else has to be the dv. You can't leave anything hanging there. So dv is going to be e to the 3x dx. Now, if this is dv, this is denoting a derivative. So if you kind of compare that to what we had here, you had an original, you took the derivative to get down here. We're going to do the opposite to get v. We're going to need v because remember that in our formula, we need u, v, v, and du. So we have a u, we have a du, we just need v now. Technically, we don't even have to have dv for this, but in order to get to v, we had to write down what dv was. So let's go ahead and say that v then has to be the integral of dv. So v is the integral of dv. Remember the derivative and the integration symbol are sort of like inverses. They kind of cancel each other out. So that's where we're going to get your v. Now you don't have to write this particular step. You can just integrate, but I just want you to see what I'm doing and where that came from. And then when we integrate this, we'll get, I'm going to use that rule here, 1/3 e to the 3x. Now, normally we would put a plus c on this, but when we're using this, we'll put a plus c on the end when we get to the end of our integral. Do that. And we're not going to use it now. Okay. So that's the hard part. Now it's just putting it all back together again. So what we're going to do is we're going to turn our integral of u dv into uv minus the integral of v du. And the goal is that this integral, because you might be thinking, why would I write an integral as another integral? This one's going to be simpler. It should be one that you already know how to work your way through. Don't forget, if you pull this constant multiple out, don't forget that it's out there. You're going to have to use it again. Okay, so I'm going to bring this 2 down, and then I'm going to sub out this whole thing. Instead of having it be u dv, I'm going to write it as uv. So, and when I multiply these together, I'm going to put the 1/3 in front. And just sort of rearrange the order because multiplication is commutative. I can do that. So this will be our uv And then we're always subtracting here. And then we'll take the integral of v du. So 1/3 e to the 3x, and then du is dx. Now you're going to find that when I go through this, I'm going to write extra stuff just because I really want to make sure everybody knows where I'm coming from and everybody can see all of my steps. So this 1/3 being inside the integral, yes, it's going to drive me crazy. I'm probably going to pull it out in the next step. I'm probably even going to distribute the 2 so I don't forget about it, or it maybe doesn't get distributed to both terms. We'll probably do that next, but this is the integral of v du. Okay, so there's your v, and here's your du. But notice now that what happened was when we rewrote v du, well, now there's no x here anymore. And now this is an integral that you know how to work with from Calc 1 using either u substitution or this formula. So that's kind of why we used parts so that we could simplify this integral down to something that we already knew how to deal with. So let's go ahead. I'm going to write this as distributing the 2/3 x e to the 3x minus, and I'm going to pull this 1/3 out, and I'm going to call it 2/3 when I distribute the 2, the integral of e to the 3x dx. Okay. And then the last thing I need to do here is just integrate. So I'm going to leave the first term as it is, 2/3 x e to the 3x minus, and then 2/3, and then we already know how to integrate this. We did it before, so we're just going to do it one more time. This integral right here is going to be 1/3 e to the 3x, and then we're always going to pop up plus c onto our answers here for our indefinite integrals. And don't leave it like this. Of course, you want to have all of this multiplied in. I know it just seems like, oh, I have to keep rewriting it. Yeah, you do. It's good for you. When you start to skip steps because you don't want to write stuff, that's when things get lost. And that's when you make what everybody refers to as stupid mistakes. Students are always telling me, oh, I looked over my test and I just lost all these points for these stupid mistakes I made. Sometimes it's just because you weren't writing down enough information, skipping steps, trying to do mental math, and stuff got lost or things got written funny. And as a result, errors were made. All right. So this is actually your answer, the box around it. So if I were to ask you, what was this integral equal to? You would tell me it's equal to 2/3 x e to the 3x minus 2/9 e to the 3x plus c. So that is how you would integrate a function that looks like that. I'm going to do another example that's a little bit more basic like this, but you're going to see that in a lot of the examples that we work with, you're mixing two different types of functions together. So in this case, for example, 1, you had an algebraic function and an exponential function. In the next example, I'm going to give you an algebraic function and a trig function. And then we'll sort of work our way through into slightly more complicated things. It's not going to get super crazy in here, but there is especially there's one technique that's especially important that we're going to get to. Everything else is going to be pretty straightforward. Every once in a while, you're going to come across something where you're just not sure what u should be or what dv should be, and you might have to put a little bit more thought into it. But I'm going to try to show you some examples of what could happen so that you're ready for if that occurs. Okay, so that was example 1. Example 2. All right, so this is the integral of x times the cosine of x dx. So like I said, this one's going to be pretty similar to the last example, except in this case, you have an algebraic function, or in this case, some linear function in x multiplied by a trig function. The last example, you had an exponential function. But u, in this case, is going to be your algebraic function, x. And if you're not sure, remember, go back to your Lyot. What's my Lyot sheet? Logarithmic, inverse trig, algebraic. Algebraic comes before trig. And remember, you want u to be the function whose derivative is simpler than u. If I were to take the derivative of cosine x, I'd get negative sine x. It's not really any simpler. It's just going to be this cyclical situation, which you're going to see in a few minutes what we're going to do with a situation where we have no choice when we have functions that are cyclical. But in this case, we have an option here where a function has derivatives that eventually are going to head down to 0. So we're going to let our u portion be x. And then dv is going to be the rest of the integral. So remember, I'm trying to match this u dv formula. So dv will be cosine x dx. Don't forget your dx because it's technically part of your dv. And when you integrate it, that dx is going to pop off anyway. Du is just 1 dx because the derivative of x is 1. And then v, you are integrating to go from your derivative up to the original function. The derivative of sine x is cosine x. Therefore, the integral of cosine x is sine x. Be really careful with that. What happens a lot, especially with these integration by parts problems, is, excuse me, students tend to miss the sign on these, S-I-G-N sign, and they'll integrate this wrong. Either they'll forget to write a negative or they'll write a negative when there shouldn't be one. They treat it like it's a derivative, for instance. They'll say, okay, well, the derivative of cosine is negative sine. Well, that's not what you're looking for. You're looking for the integral of cosine x. So just be careful here because that will throw off your answer. And in some cases, it's going to throw off your answer by a lot, not just like a sign. So be careful there. All right, now we have u, du, dv, and v. That's great. Remember your formula. The integral of u dv equals uv minus the integral of v du. You're going to use that so often, you're not even really going to think about it anymore. So I'm going to rewrite this as uv, which is x times sine x. Okay, so that's uv minus the integral of v du, so sine x dx. Okay, so we've now rewritten our original integral by using parts. And when we integrate the next time around, we won't have to use parts because now we just have sine x and we already know how to integrate sine x. By using parts, we were able to split off this algebraic function that was causing us to not be able to integrate this using techniques that you learned in Calc 1. So this is going to be x sine x. And the derivative of cosine x is negative sine x. If you need to think backwards, kind of think about it this way. Remember that your original function in this case was sine x, and then you took the derivative to get to cosine x. What you're doing here is the opposite situation. You're looking at your derivative and you're trying to get back to the original. So if your derivative was negative sine x, then your original would be, or I'm sorry, I'm saying this backwards. If your original is sine x, then your derivative is going to be cosine x. And if your original is sine x, then your derivative would, if your original is cosine x, your derivative is negative sine x. You have a positive sine x, so you're going to go here with negative cosine x. Sorry, I should have just prompted you to use your formulas there for integration. But you can always go back and check this. Like I said, this is one of the most common errors that students make. You should be able to look back and make sure that you get back what you started with. You'll do that by taking v and making sure you can get back down to dv. So the derivative of cosine x is negative sine x, but you don't have negative sine x, you have positive sine x. So the derivative of negative cosine x is positive sine x. If you feel like, oh my gosh, I can't remember which one's which, you have a formula sheet that I gave you. It's uploaded onto D2L. It's under content. Also in the front cover of your text, there's a whole big formula sheet for integrals and derivatives. Feel free to look at that. If you just feel like you want to double check, where you're like, oh, I should know this, but I just want to double check, that's fine. Look at it, double check. I would hate for you to have that be wrong. It'd be terrible. Okay, and I'm just going to simplify this by using addition. We have x sine x plus the cosine of x plus c. Wait on that thought that I was going to give you just now. Okay, that was example 2. Example 3. This is the integral of x to the 2/3 ln x dx. Now, you did not even learn how to integrate ln x when you were in Calc 1 because the integral of ln x dx actually requires parts. So you can do that whole integral using parts. And in this case, you're going to have to do that also. I kind of want to do just ln x. Let's do that first. I'm going to call this side note. This is one that you're going to see a lot. If you don't see it like this with ln x dx, you might see it as an inverse trig function. So like maybe the inverse sine of x or the inverse cosine of x dx, so on and so forth. These are the special Lyot ones that come first. L is for logarithmic. So if you had this function, you would definitely let u be the logarithmic function ln x. But I think what students have a hard time with here is they're like, well, if u is ln x, then that leaves nothing. That's not true. If u is ln x, that still leaves dx for dv. Okay, so we'll integrate this one real quick just because it's one that you're going to see more frequently than you might imagine. So it's okay if dv is just dx. That's going to happen sometimes if you only have one function inside your integrand. All right, so the derivative of the natural log of x is 1 over x dx. That you learned how to do in Calc 1. And then if dv is dx, integrate both sides and you get v equals x. So the integral of ln x dx will be uv, which is x ln x, minus the integral of v du. So v is x and du is 1 over x dx. And this is really x ln x minus the integral of dx because you're going to get these x's to cancel inside the integrand. So we have x ln x minus x plus c. This might be on a formula sheet somewhere for the integral of the natural log of x dx. It's x ln x minus x plus c. You might use it so often that you remember what it is. But if I gave you just this integral, I would want you to use parts for that. Okay, back to example 3. I just wanted you to have a good sense of what would happen if you just had one, what looked like one function inside the integrand. So for in this example, you would let u be ln x, because logarithmic, that's your first choice for u. That's what you're going to use most of the time, as long as dv was still a function whose integral you could take. So that means dv would have to be whatever else was left, which in this case would be x to the 2/3 dx. Well, u would be, or I'm sorry, du would be 1/x dx. And then v would be the integral of dv. And when we integrate a power function, we just take our exponent, increase it by 1, and divide by the new exponent. So 2/3 plus 3/3 is 5/3. So you would have 3/5 x to the 5/3. That was our side note. Now we're going to go back down here. And we'll say that the integral of x to the 2/3 ln x dx is equal to uv. And again, multiplication is commutative, so I'm just going to put the constant multiple in front. And actually, you know what? I'm going to keep the x to the 5/3 in front too. ln x minus the integral of v du. Now, if you already know, okay, I'm going to be multiplying these together and I'm going to be putting them inside this integral, be careful with your mental math. I usually write this out and then I simplify it in the next step before I reintegrate. So uv minus the integral of v. So v, we said was 3/5 x to the 5/3. And then du is 1/x dx. So there's your uv Wait, I said that backwards. Sorry. It's actually v and u, but that's fine. Minus the integral of v du. And then simplify that integral portion in your next step. So there's really nothing that you need to do here with this first term. If you want in the integral, you can take that 3/5 out as a constant multiple. X to the 5/3 divided by x really just means that you're taking 1 away from the exponent. Well, you already know how to do that because it's what you originally had. So x to the 5/3 minus 3/3 is x to the 2/3 dx. And that's just because you took x to the 5/3 and divided by x. Using exponent rules, you end up with x to the 2/3. And again, the nice thing is you already took that integral. So in the next step, you don't need to do that again. You can just look at your work and rewrite that. So you'll have, minus 3/5 times, and then this integral we said was 3/5 x to the 5/3. So we'll do that again. And then the last thing we need to do is just multiply the 3/5 times itself. So you'll have 9/25 x to the 5/3 plus c. I don't need you to go factoring things out. You can if you would like, but it's certainly not necessary. So that was an example of an integral that had a logarithmic function in it, which I think is good to do anyway. We don't take a ton of derivatives of natural logs. Example 4 All right, so this one is going to be a little different. This one is x squared cosine 2x dx. You might be thinking that this looks basically like what we did for example 2. And it's similar, I'll give you that. But in example 2, I mean, there's a small variation here in that this time we have cosine 2x instead of cosine x, but that doesn't change the solution process. What changes this is the fact that we have x squared instead of x. And maybe that doesn't seem like a big deal to you. You're like, yeah, it's still algebraic. Okay. Well, watch what happens when we go to work on this with parts. There's a reason why I'm doing this example, not to just repeat stuff we've already done. So you still want to let u be, in this case, the algebraic portion. dv is going to be cosine 2x dx. Because remember, we're trying to get to that simpler derivative, and we do indeed get a simpler derivative. The derivative of u is 2x dx. So we are making this simpler. Now, when you integrate v, the derivative of sine is cosine. And I'm going to give you this same formula that we used. I gave it to you in class for, I don't remember when it came up, but we talked about it. But it's basically the same idea as what I gave you over here. It's just for cosine and sine functions for if you have a kx. So we would say that the integral, side note, the integral of cosine kx dx is going to be 1 over k sine kx plus c. The derivative of sine is cosine. But you're just taking whatever that constant multiple is in front of the x and dividing by that in front of the function. And this works the same if you're dealing with sine. This will just be negative 1 over k cosine kx plus c. The derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. But you can feel free to use these. I hope it wasn't an office hour when I originally gave those. I don't think it was. But anyway, use these ad nauseum throughout the section, throughout the chapter. All right, so your integral here is going to be 1/2 sine 2x. And like I said, this is a place where students tend to get their signs, S-I-G-N-S, incorrect. So make sure that you have the correct sign on this. If you need to, put this on a note card, have it nice and bold or highlighted or something so that you see it and you know which one's which. Okay, so we're going to put this back together again. So here's what we started out with. The integral of x squared cosine 2x dx. So what we're turning that into is uv. And again, I'm going to multiply these. Multiplication is commutative. I'm going to put the 1/2 first. Then I'm going to put the x squared, then the sine 2x. You don't have to do that. I just think that is what looks best. I certainly wouldn't put the x squared behind the sine 2x. You don't want to accidentally multiply those together and call it sine 2x cubed. That would not be the same thing. All right, so that's uv minus the integral of v du. And you know what? There's not like a whole ton going on with your v du. So I'm going to pull this 1/2 out. And then your v du is going to be, oh, you know what? I still do have the 2, but that's okay. I'm going to write this one more time anyway. 2x sine 2x dx. So this is the integral of v du. We'll simplify that a little bit. So this is really just the integral of x sine 2x dx. Now, in the previous 3 examples, when we've gotten to this point where we've applied integration by parts and we've sort of split this up and we've gotten the integral of v du, the integral of v du has always been something that we knew how to integrate. That's not the case here. But notice that we're close. Right now, the integral of v du looks very much like what we started out with in example 2. In example 2, we had x cosine x. Sorry, I'm looking way at the bottom here. X cosine x dx, and this time we have x sine 2x dx. So whether it's 2x or x doesn't matter, but you can see now what the problem is. You still have a situation where your integrand contains a product of 2 functions. If that's the case, you don't know how to integrate this. You're going to have to use parts again. So there might be examples where you're going to have to use parts 3 times. I mean, imagine if this was x cubed cosine 2x or x cubed cosine x or anything like that. In order to get from x cubed down to a derivative that doesn't have a variable in it, you're going to have to use parts 3 times. But in this case, in order to get from x squared down to down to a v du that doesn't have a variable, you're going to have to do parts 2 times. So we already did parts once. So we're going to use integration by parts again. And we're just going to be really careful here to make sure that we don't screw up our expression. And I'm going to write out different u, v, du, and dv's. So the ones that we used back here are done. Don't look at those anymore. We've used them. What we're going to do now is look at this integral of x sine 2x dx and look at u, v, du, and dv based on that. So I'm going to let u be x and du is dx, which is awesome. And then dv will be sine 2x dx. V, the derivative of cosine is negative sine. Therefore, I'm going to put a negative on this 1/2 cosine 2x. Or you can always look at this formula that I gave you. Okay, now, when we do parts again, we're just going to keep the original uv on here because really all we're doing is looking at parts with this piece of the integral, just with this term. This is still included in the answer for the integral for x squared cosine 2x dx. So I'm going to rewrite this 1/2 x squared sine 2x that came from there. I have a minus sign that I'm pulling from there. And then this whole integral goes behind the minus sign. Be very, very careful here. Be very careful. Like in case you have this muted and you're just looking at the notes, I want you to like maybe see my eyes and then I'm doing something crazy and then you're like, what's she talking about there? Well, what I'm trying to do is emphasize that this minus sign is going to have to get distributed because you're going to have more than one term behind it. So we're going to take off this whole integral, which we're going to rename as uv, so minus 1/2 x cosine 2x, and then minus, because integration by parts is uv minus v du, or minus the integral of v du, I should say. V is negative 1/2 cos 2x, and then du is going to be dx. Okay, so there's your v du. And now we're going to simplify, and luckily we're going to have something here that we can integrate using rules from Calc 1, and we won't have to use parts again, because this time I don't have any sort of constant multiple that has a variable in it, which it wouldn't be a constant multiple in that case, but I don't have any variables that are being multiplied into this function. So we have 1/2 x squared sine 2x plus 1/2 x cos 2x. And then be really, really careful here. Because, okay, so this is where my plus came from, negative times a negative. But watch what happens here. I have two negatives, and two negatives make a positive, and then I have one more negative. If you have an odd number of negative signs, it's going to stay minus. And then I'm going to pull that 1/2 out front, and I have the integral of cosine 2x dx. And this we can integrate. So I'm going to rewrite everything else, and I know you're going to get tired of rewriting all this stuff. Sorry, I don't have a solution for you. It's going to get tiresome, but you're going to have to write it, because if you don't write it, stuff's going to get lost. And you're going to be like, oh, emailing me saying, I'm just like busting my head open over this homework problem I cannot figure out. I keep entering my answer and it's not right. Gotta write every step down. The derivative of sine is cosine. So 1/2 sine 2x. And we actually already did that integral anyway. So we're almost done with this one. Writing it again. So plus 1/2 x cos 2x minus 1/4 sine 2x plus c. Sorry, this looks like a v, but it's definitely an x. Don't feel like you need to go factor a bunch of stuff out of this. I know that you have at least in common a sine 2x. You have some algebraic pieces in common. Well, I guess technically you have some constant multiples where you could pull things out. I'm not too worried about it. If I were you, I'd leave it. Don't get too crazy with it. All right, so that was example 4. That was an example where you needed to use integration by parts twice. Let's see. All right, so another type of example that you're going to see here is this issue where you have two functions that are cyclical, that have cyclical derivatives, I should say. And this is a very, very, very common type of parts problem. And usually they involve the same type of functions every time you see them. We'll call this example 5. So this is going to be the integral of e to the x sine 3x dx. Now, your choice of u and dv, I mean, it's kind of up to you in this case. If you're thinking along the terms of Lyot, you would be thinking, okay, like let's maybe let the trig function be u. And that's fine. We can do that. If you want to, you could also let e to the x be u. And even though you're thinking, well, Lyot, e to the x would come last, that's true. But what's going to happen here is no matter what, either one of these functions whose derivative you take, you're going to end up with another function that's similar to that. So the derivative of sine 3x is going to be 3 cosine 3x. So not really changing anything, certainly getting more complicated in that case. It kind of depends on which one you want to take the derivative of and which one you want to integrate. But we're going to have to use a special technique here because you've got two functions where if either one of them is not a good choice for you, really, because you're derivative is not going to be any simpler than the original at all. And then when you take dv, you do know how to integrate in both cases. Let's go ahead and we'll let u be the trig function. And we'll do that just because I don't know, I'm just thinking lie it. I just want to do what you guys would do. But you might want to, if you're going through this and you feel really comfortable, you might want to let u be e to the x if you prefer, and just verify that you get the same thing. You will, but it's not going to matter in this case. But I'm going to show you a special technique that we use anytime both of these functions have derivatives that don't terminate. So like a terminating derivative, I mean, normally, like if you have x squared, for instance, you take the derivative, you get x, you take the derivative again, you get 0, and there's nowhere to go from there. That's why you know that that's such a good choice for you. In this case, your derivatives are just going to keep going and going and going for all of eternity. That's why I have to show you a special technique for this type of problem. So we'll let u be the trig function. And then we'll let dv be the other part of the function, which in this case is going to be e to the x dx. Now, when you take du, remember you have to use the chain rule. So you're not using that integration formula where you're taking 1 over k. This is going to be 3 cosine 3x dx. So you're multiplying by the derivative of the inside function. And then v is just e to the x because the integral of e to the x is e to the x. Okay. So we're going to end up going through parts twice, and then I'm going to show you the technique, the special technique. It's not that big of a deal. It's just a step that students, for some reason, have a hard time remembering to do. So I want to make sure I make a big deal about it when we get there so that you remember, like, oh, wait, this is what I'm supposed to do now, because it's a different sort of technique. Okay, so far, this is the same as what we've been doing. We're going to go ahead and apply the parts here. I'm going to keep writing the original function on the left-hand side. I've sort of been doing that throughout, but you're going to see why we really want it there in a couple minutes. Okay, so let's do uv. So e to the x sine 3x is your uv minus the integral of v du. Du has a constant multiple of 3 on it, so I'm just going to pull that 3 out front. So we have uv minus the integral of v du. So e to the x cosine 3x dx. Okay. So you're going to apply parts again now. And I'm going to show you why in a minute, because you might be thinking like, okay, well, this really doesn't look like it changed. If anything, it looks more complicated because now it has 2 terms instead of 1. I'm going to show you what we're going to do here. Do parts again. Use the same u and v types of functions that you used before. So we're going to let u be, in this case, the cosine of 3x. And then dv will be e to the x dx. So the derivative of u is negative 3 sine 3x dx. And then the integral of dv is e to the x. Okay, now a lot of the mistakes that happen here happen with signs, distributing, and those are really the 2 main things. So be careful here. Here's my original. This term comes down, e to the x sine 3x. And then the piece that we were working on parts with, again, is this one. We left the 3 on the outside, and then all the parts happen inside the integral. So that 3 is going to end up getting distributed in with the negative in front of it. So uv is e to the x cos 3x, and then minus the integral of v du. So this is going to get not crazy, just like you got to be careful. So I said v du, so the du and the v, there's that whole thing. I'm going to watch my grouping symbols. So this whole thing is the integral of e to the x cos 3x dx. So here was uv, and then this was the integral of v du. Okay, we're going to simplify before I show you what the special technique is. No, I keep talking about it. You guys cannot wait to get to it because it's going to be so cool. All right, so the first term doesn't change. The second term becomes minus 3 e to the x cosine 3x. And then in the third term, you have 1, 2, 3 negative signs. So that's going to stay negative. And then you have the 3 that gets multiplied in. 3 times 3 is 9. So we're taking minus 9 times the integral of e to the x sine 3x dx. This might be one of those spots where you want to pause the video, look over it again, make sure that everything's accounted for, make sure that you understand where everything came from, so on and so forth. Okay. So here's where the special technique comes in. Once you apply integration by parts twice, what you're going to see is, and by the way, you're going to see this because you kept rewriting your original, where is it? On the left-hand side. You're going to see that you get some integrals that match. So you have your original integral equals, and then you did parts once to get this. The second time, this term popped out, and that one popped out from doing it the second time. Since these two match, what we're going to do is add these terms to both sides. We're going to solve the equation. I'm going to say solve this equation. For the integral of e to the x sine 3x dx. I mean, that's what we were trying to find, right? This thing. So we've got an equation here. We said, okay, here, this is equal to this, which is, subtract off this and that. If I want to isolate this, I need to gather all of the like terms together and then simplify. So what that means is I'm going to add 9 times the integral of e to the x sine 3x dx to both sides. I know I have like this equation here with like a sentence in the middle of it. It's very bizarre. So when we added 9 of these on both sides, well, you had 1 plus 9 more. You now have 10 of them on the left-hand side. And then on the right-hand side, you have whatever was still over there. But now this term is gone because you added all 9 of these to the left-hand side, or to both sides technically. And now you're almost done. And if you're not sure why, well, here's what we were trying to find, right? The integral of e to the x sine 3x dx. That's originally what I asked you for. But I didn't ask you for 10 of them. So at this point, I'm going to write this again just so it looks super clear on my notes. I'm going to divide every term by 10 so I can get that integral by itself, because this is what I was looking for. And I have to divide, when I divide both sides by 10, I'm really dividing every term by 10. And then you'll just rewrite this into a way that looks nice enough for you. I mean, technically, this is fine. You just would need to add your plus c onto there. We have 1/10 e to the x sine 3x minus 3/10 e to the x cos 3x. Don't forget your plus c. Okay, so when you see this type of problem where there's really no good u to choose because the derivatives are just going to keep giving you that same type of function over and over and over again, that's fine. Use this process. A lot of times you will see it with an exponential and a trig. It's just the way it is. Okay, now I had one that I wanted to do that was just a natural log, but there was some more interesting stuff in it that I thought would be good to remind you of. So we're going to do that next. So this will be example 6. Sorry, I lost my page. I have a plethora of examples here that I like to sort of leaf through and figure out which ones to show you. I also wanted to do this one because it has a definite integral, which you can still use with integration by parts. And just due to the nature of the function, I thought it would be a good one for us to go over. Okay, so I gave you an example before where we were looking for the integral of the natural log of x dx. So this is same idea, but this time we don't just have the natural log of x. So, but we're still going to let u be the natural log function. Logarithmic comes first. That's your first choice for u. And then dv will be dx, just the other piece that you don't have included in your u. So here's your u and your dv. All right, so the derivative of u, remember the derivative of the natural log of u is u prime over u. So you're going to take u prime and divide it by itself. Sorry, I said u prime, but what I meant was this function as being u. When you're given this as a formula in Calc 1, it's natural log u. I know now I have so many u's going on that it seems confusing. Another way of saying this would be the derivative of the inside function divided by the original. We said that a lot too. So the derivative of the inside function is going to be 2x, and the original is 4 plus x squared. And then don't forget your dx. And then v is going to be x in this case. Now, forget for a minute that you have a definite integral. We're going to use it, but you're not going to do much with it right now. All right, so go ahead and set up your parts. We have uv, so I've got x times ln 4 plus x squared minus the integral. You can pop your limits of integration back on from 0 to 1 of so it's uv minus v du. So your v du, when you multiply these two together, I'm kind of toying with, do I want to pull this 2 out front? And I kind of do. I'm going to move the 2 out front. But uv minus v du, when I multiply these together, The 2 I'm going to pull out from the integral. I just did that. And then in the numerator, you'll have x squared because you'll have x times x. And then the denominator, you'll have 4 plus x squared. We have a dx. Okay, now it's up to you if you want to include this notation, but since you have a definite integral and you already evaluated this piece, you might want to note that just by putting this evaluation bar on here. I'd probably wait until the end to evaluate it, but it is a variable expression. It did pop out of your integral. You will have to evaluate that from 0 to 1 at some point. Whether you do it now or later is immaterial to me. I'm going to hold on to mine for now because I really want to focus on integration. Okay, now you're going to have to focus on how to solve this integral. And if you're thinking like, oh, it looks like a u substitution. If you let u be the denominator, then du is 2x. Well, you've got more than that up here. So it's a situation where you have too much. I'm kind of disappointed because your Sullivan book for Calc 1 didn't really give any instruction on what to do when you had this situation. And this situation is a situation where you have a rational expression where you have the same degree in the numerator and denominator. So I'm going to write down what to do now. When your integrand is a rational expression, remember a rational expression is a fractional expression. So when your integrand is a rational expression where the degree in the numerator equals the degree of the denominator, use long division to simplify. You will find that you are going to need long division for something like this. If you don't remember long division, I'm going to remind you right now. We're taking x squared and we're dividing it by 4 plus x squared. If you want to write that as x squared plus 4, that's probably for the best. And then you have 0 x's and 0 constants under your in your dividend. All right, so for long division, you're taking the first term in your dividend and dividing it by the first term in your divisor. X squared divided by x squared is 1. I like to line the constants up. You don't have to. 1 times x squared is x squared. And then 1 times 4 is 4. So you always take this value that you got using division and you multiply it by both of these values in the divisor. And then you subtract. So x squared minus x squared is 0 x squareds. Then I have 0x minus nothing, still 0x, you don't have to write it. And then 0 minus 4 is negative 4. Okay, now you'll know you're done with your long division when the degree down here in your remainder portion is less than the degree in your divisor. So if I take negative 4 and divide it by x squared, I'm going to end up with x's in the denominator. So I know I don't need to keep working on long division here. That's how I know I have a remainder. So I would say this is 1 minus 4, and then you're always writing your remainder over your divisor. So we have 1 minus 4 over x squared plus 4. Okay, so back to the integration. I'm going to go back here. I'm kind of torn on whether we should just evaluate that and not have to worry about it anymore. Sure, let's do that. Note x times the natural log of 4 plus x squared. Since we're already off on this tangent, we might as well go ahead and evaluate this now. So we're going to use the FTC. to evaluate this first term, and then we can just carry some constants or whatever it is around with us and focus on this integral. So this will be 1 times the natural log of 4 plus 1 squared minus, and then 0. It's 0 because you have an x here. But notice if you didn't have this x here, you'd have the natural log of 4 plus 0, which is actually the natural log of 4. So be careful with that. Don't just always negate it. So 4 plus 1 squared is 5. So we have the natural log of 5. So I'm just going to replace this now when we see this next in our integral with just the natural log of 5. It's just less that we'll have to worry about later. So we now have the integral from 0 to 1 of the ln of 4 plus x squared dx is ln 5, which we obtained from this quantity. So that was up there. And then we have minus 2 times this integral. And what we did here was we split this up. Since we had the same degree in the numerator and denominator, we rewrote it. And if you're not sure why, well, now we're in a form we know what to do with. I'll tell you what it is in a minute if you don't recognize it. So this is the integral from 0 to 1. And we rewrote x squared over 4 plus x squared as 1 minus 4 divided by x squared plus 4. So this, remember, was the quantity x squared over 4 plus x squared. We just rewrote it into an equivalent form. Okay, so I'm going to split this up because I have 2 terms. This one's easy to work with, so I don't want to keep carrying it around for nothing. This one is what we're really going to focus on. This is an integral that we worked on in Calc 1. So we're going from 0 to 1 of ln 4 plus x squared dx equals ln 5 minus twice the integral from 0 to 1 of 1 dx. And then I'm going to distribute this -2 into my parentheses. So -2 times -4 is +8. And then I have the integral of 1 over x squared plus 4 dx. Okay. So remember that anytime you're looking at an integrand that has 2 terms in it, you can integrate each term separately. Okay, so we split up the 1 and we split up the 4 over x squared plus 4. Wonderful. This one we can go ahead and compute if you'd like. If the 1 being missing is bothering you, you can always pop it in there. So we have ln 5 minus 2 times the integral of 1 dx is x. We'll take that from 0 to 1. And then plus 8 times the integral of 1 over x squared plus 4 dx. And of course, this will be 2 times 1 minus 0, which is just 2. We have ln 5 minus 2 plus 8 times the integral of 1 over x squared plus 4 dx. This is a Calc 1 integral. If it's not popping out at you, I'm going to say recall from Calc 1. You had the integral of 1 over, it was either 1 plus u squared or u squared plus 1, doesn't matter. Du is equal to, I'll give you a second to think about it. Which one? is equal to the inverse tangent of u plus c. Wonderful. However, when we did this in Calc 1, we were looking for this constant value in the denominator to be equal to 1 so that we could completely match this up. We don't have that, so we're going to have to create it. So we are going to focus now on creating this situation. So I'm going to bring this integral out for now. Just the integral. The 8 can stay right where it is. What you're going to do to create a 1 here, to get this into this form, we're going to make it a 1. You're going to divide every term by 1. So we're going to rewrite this, I'm sorry, divide it by 4, not by 1. 4 divided by 4 is 1. Everywhere in every term, you're going to divide by 4. And this is going to leave you with, and I'm going to pull that 1/4 out front from the numerator. Doesn't need to be in the numerator. I'm going to put it in front of the integral. That leave me with dx in the numerator. And then I do have that plus 1 that I'm looking for in 4/4. And then I need to write this as a quantity squared. I have x squared over 4, but I want this to be in the form of u squared. So I need that whole quantity to be squared. Right now, only the x is being squared, not the 4. So you're going to rewrite this as, well, the square root of x squared is x, and the square root of 4 is 2, quantity squared. So now if you take x over 2 and multiply it by itself, you get x squared over 4. Now you're in the form that you need to do a u substitution. I know this problem is just the gift that keeps on giving, isn't it? I actually had second thoughts about doing this one, but then I was like, oh, you know, there's a lot of good stuff in one problem. We might as well. I would hate for you to miss out on all the technique and all the refresher from Calc 1. All right, so we're going to let u, now we're into a u substitution here. This is no longer a u that has to do with parts. We're going to let u be x over 2, or 1/2 x. And then du is 1/2 dx. We only have dx, we don't have 1/2 dx. So we'll say 2 du is dx. And then we'll sub it out. So we have 1/4 from your constant multiple. We have dx is 2 du. So the 2 I'll move in front. And in the denominator, I have u squared plus 1. Two over 4 is 1/2. And then I have the inverse tangent of u. This is going to be a definite integral. I forgot all about the limits of integration. I stopped writing them for some reason. Technically, they're supposed to be up here, and here, and here. If you want to just back substitute and pop your original limits on, that's okay. I know I made a big stink about it in Calc 1 about how I wanted you to change the u limits, but there are so many u's going on right now, so let's just switch it back and not worry about that. So you have 1/2 inverse tangent of u, which is 1/2 inverse tangent of x over 2, or 1/2 x, whatever you want to say. And then we'll put this back into the original integral and use the FTC to evaluate it now, because we're almost done with this one. Okay, so this whole piece right here was what we were working on below. Okay, so I'm going to go back to my original now. So I have ln 5 minus 2 plus 8. And then this whole integral we found to be 1/2 inverse tangent x over 2. And then we'll go ahead and evaluate that from 0 to 1. ln 5 minus 2 plus 8 over 2 is 4. Inverse tangent 1/2. This is going to be the same no matter what. The only thing that's changing now is we're using the FTC to turn this into 2 terms. So the first one will be 4 times the inverse tangent of 1 over 2, and then we'll subtract off 4 times the inverse tangent of 0. The inverse tangent of 0 is 0 because the tangent of 0 is 0. Remember, when you're looking at an inverse tangent, you're asking yourself, what angle has a tangent value of 0? Well, that would be 0. You can also pop that into your calculator. Inverse tangent 0 is going to be 0. So this guy goes to 0, and what you end up with here is ln 5 minus 2 plus 4 inverse tangent 1/2. And you can stick a box around it. It's done. I feel mean for giving you that example, but there was just a lot in there that I thought was good stuff. I know it's just packed all into the same example. Let's see, I have a note here. I totally forgot that I had this note, or I would have considered it sooner to go over this problem. I just don't know if it's necessary. Let me take a look at it. Somehow missed this note. Maybe. Yes. We should go over that problem. Okay. What about this problem? So we're going to do one that uses a double substitution. Yeah, I guess there were just a couple with some double substitutions. One would probably suffice. Okay. We'll do that. Sorry, I missed my note to self earlier. Maybe I'll do 2 of these because there's also one with a definite integral, and we can keep my eye on the time here. Let's do the first one and see how much time we have left. So this is a double substitution. Yeah, I do think this would be a good one to go over. I think your homework will probably have one that has something like this in it, but maybe not something like the next one. Let's do this one. Probably do this one and call it a day. Which I hate to say that, because what if I change my mind? This will be example 7. This is the integral of x cubed e to the x squared dx. Okay, so this one's a huge mess, and the reason for that is, let's say you're looking at this and thinking about it in terms of a standard integration by parts problem. And you'd be thinking, okay, well, let's let u be x cubed And then dv is e to the x squared. And as soon as you say that, you're kind of like, wait. I can't let dv be e to the x squared because I don't know how to integrate that. And if you tried, I mean, okay, so here's what I would say you would try. You would say, okay, let's let u be x cubed. Du is 3x squared dx. And right off the bat, you would already kind of know this isn't good because I at least need to do parts 3 times at best case scenario. Okay, so then you would say, let's let dv be e to the x squared dx. V is the integral of e to the x squared dx. And then you're stuck. You're kind of just like, well, now what do you do? Because then you would say, well, let's let w, I don't want to use u again. That's why I'm using w. You would say, well, let's let w be x squared, like assuming that you're going to use a u substitution for this integral, and dw, which we know I don't care for because of that show, is 2x dx. And then you would be like, well, I don't actually have 2x dx. And then you'd be in this bind. And then what would you do? So you're kind of going through this and wondering where your path out of this would be. One thing you have at your disposal, if you have w equals x squared, you have dw equals 2x dx. Well, then you would have to create something else in there to cover your missing piece. And you would be stuck. So let's say we keep this substitution and we say w equals x squared, dw is 2x dx. Well, try to build something that is reflective of what you have. For instance, if I divide both sides of this by 2, I just kind of want to focus on this piece right here. Then we would have 1/2 dw is x dx. Okay. Now, if we have x dx and we want to come up with x cubed dx, we're going to have to multiply that out. And you might be wondering, why would I want to come up with x cubed dx? Well, I'm focusing right now on what we have here. So let's try to piece this out here. I don't want an x dx. I want an x cubed dx. So we're just sort of going to rewrite this integral without thinking about it in these terms. So I'm going to write 1/2 x squared dw is x cubed dx. We did a technique like this during the first week of class. I want to say not the first day, because the first day I went over the syllabus. I think, yeah, it was the second day that I went over the integration review, and we did some integration that looked kind of like this. So if you're trying to come up with this piece, you're going to have to multiply through by x squared, and then you're like, wait a second, this is not going to work for me because I have an x and a w in the same expression. And that's when you pull this back in here. And you say, okay, well, 1/2, if I know that x squared is equal to w, then you say w dw. Our favorite Arthur character is x cubed dx. And you might be wondering, what the heck does this have to do with integration by parts? Well, we've used this substitution to rewrite the integral, and then we're going to pull the parts back in. So chuck that, keep this. Okay, so when we rewrite this, we have an x cubed dx equal to 1/2 w dw. That's your x cubed dx. And then e to the x squared, in this case, would be e to the w. And you would sort of just rewrite your integral using that new substitution. Now, this is something that you would try to do anytime you don't know how to integrate v. So you kind of have this crazy expression you don't know what to do with. That's when you need to try to think about a way to rewrite the integral that you have in simpler terms. And mostly, if you weren't sure about where to come up with this substitution, I mean, think about what's actually causing you the problem here. The problem is the x squared because you have never integrated e to the x squared. So you're kind of like, okay, the square is the problem. If it was just e to the x, I would be fine, but it's not just e to the x, it's e to the x squared. And that's where this substitution comes into play. Just kind of trying to rewrite that integral. Okay, so we've rewritten the integral now in terms of w. So we're gonna now pull that 1/2 out and we'll say this is w e to the w dw. And now this looks very much like what we did way back in example 1, where I gave you 2x e to the 3x dx. All right, so now we're in more of a traditional parts problem. And if you want to keep using u and v, you might as well, because we kind of tried, we couldn't get it to work. So I wouldn't even have considered that as being part of the problem anymore. So we're going to let u be w, and then dv is going to be e to the w dw. And then du equals, du equals dw. And then v is equal to e to the w, because it's just the integral of e to the w dw. I know sometimes it's hard to integrate things anytime they include weird variables like w. Don't be thrown off by that. Just rewrite it with an x if you're not sure. Okay, now we'll apply parts to this. So we have 1/2 times uv was w e to the w minus the integral of v du, so e to the w dw. If you want to distribute that 1/2, you can. Personally, I kind of like to have all the terms separated without having to worry about that. So I'm going to go ahead and distribute mine in. And then I have 1/2 w e to the w minus 1/2 e to the w plus c. And now you're going to back substitute for your w. So we said that w way back when was x squared. So we're going to back substitute. With w equals x squared. From right here. Whoop. There it is. So we'll have 1/2 times x squared e to the x squared minus 1/2 e to the x squared plus c. And these parentheses are non-essential if they're bothering you. I don't know why I put them in there. 1/2 x squared e to the x squared minus 1/2 e to the x squared plus c. Yeah. I don't know. I feel like that's probably fine. There's one more on here that's kind of, I want to say you have a homework problem that's really similar to this. Let me see, maybe I'll just do the setup. Maybe I'll just do that. Set it up for you. Yes, I will do that. All right, one more. This is going to be another double substitution problem. But since we've already done one, the second one will be a piece of cake. This one's actually slightly shorter. Look at me, I'm trying to talk up example 8 so that you guys keep your morale together here. Gotta try to keep everybody going. This is the sine of the square root of x dx. Okay, so this one is a little bit more straightforward, I think, than the last one, just because the last one had more than one factor in the integrand. So right away, when you saw more than one factor, you were thinking parts. With this one, I don't think that you're thinking parts right away, because you're not, this is not like it's a natural log function where it's just like the natural log of something dx and you're going to let u be the natural log. This is a different scenario. So you might be thinking to yourself, well, I don't know how to integrate this. And don't think about parts for a minute. Just think about what you know about integration and what you learned about double substitutions already. And you would be thinking to yourself, like, if this was sine w, I would totally know what to do. If this was sine w, I would know that the integral would be negative cosine w. And you would be right. So we're going to do a little bit of wishful thinking here. And we're going to let this be w. So we want this to look like the integral of sine w dw. That's what we're going to try to force here. In order to do that, we're going to let w equal the square root of x. And then dw, you might want to rewrite that with a rational exponent. Good old dw is going to be 1/2 x to the negative half dx, which is going to be 1 over 2 root x dx. Okay, now we're going to start having to substitute some stuff here. So think about what you're going to need. If you want to write this as sine w, and then you're also going to need a dw, you're going to have to split this off because you're going to need to sub out a dx. That means that I need to multiply both sides here by 2 root x to get that dx. And when you do that, well, now you can rewrite this again because you already know that the square root of x is w. So this is 2w dw equals dx. And now you're starting to see where your parts are going to come into play. When you sub out your integral here for the sine of the square root of x, you're letting this be sine w. And then dx is going to be 2w dw. There's your dx. And here's your sine square root x. So you're going to rewrite this in terms of w as twice the integral of w sine w dw. You should be good at this point. I'll finish it out for you. I'm still well under the 2-hour mark, so I might as well. If you feel like, okay, fine, I've got this. She's run this into the ground. That's fine. This is my last example, so not the end of the world. But I'm going to do an integration by parts here, just because I have the product of two functions in my integrand. So we're going to let u be w, and dv will be sine w dw. I know there's so many variables running around now that it seems kind of confusing. So there's some sort of bug, and I don't want to kill it on my. Ooh. Yikes. Okay. Sorry, very distracting. Du, second time I've done that, equals dw. And v is going to be negative cosine w. Oh, and no dw. And then we'll just go ahead and rewrite this using the parts. This is kind of, I want to split this off just because this is my substitution information, which is separate from what's going on with my parts. So 2 times the integral of w sine w dw equals twice uv, which is going to be negative w cosine w minus the integral of v du. And then I'm going to distribute. Negative 2 w cosine w. And then I have 2 negative signs here, so I'm going to write this as plus twice the integral of cosine w dw. Okay. And then I'm just going to integrate, and then we'll back substitute. So the integral of cosine is sine w plus c. And then we'll back substitute. We know that w is the square root of x. And you will have, yes, positive 2 sine root x minus 2 root x plus root x plus c. And that's it. So see how you do on the homework. Let me know if you have questions over the weekend. Obviously, get started on this early. We'll work on trig integrals on Wednesday, but of course, on Wednesdays, you have a quiz every single Wednesday, assuming that you don't have a test that Wednesday. So we're going to have a quiz on Wednesday covering 7.1. It's going to have to be a little different from the last 2 quizzes because I can't really ask you as many setup questions here because this is really not quite about the setups. Well, you never know. Maybe I could ask you about U and V and all that jazz, but it seems kind of boring. So we'll see. But do reach out if you have questions. I also have an office hour on Monday from 5 to 6. It's a student hour. You're not bothering me if you come to it. It's meant for you so that I can answer your questions. Otherwise, tutoring is free through the tutoring center. Please reach out and work with some tutors. They have a lot more time on their hands than I do just because that's their job is to work with students during the day. My job is to teach you during my regularly scheduled hours and answer your emails in between when I can. But it's a lot easier for me to help you in an office hour versus trying to help you via email and typing out a bunch of mathematical responses. Okay, so yeah, that's it. That was 7-1. I hope that you have a wonderful, wonderful weekend, and I will see you on Wednesday for some trig integrals on 7-2. And then my favorite topic, 7.3, will be after that, trig substitution. Oh, I love that. I'll be really looking forward to that. All right, I'm going to sign off. Everyone, enjoy and reach out if you have questions.